Hello all. Today we'll see the beauty of -1. It is a presentation. I'm giving. Okay. If there are any question, you can ask after the presentation. -1 is really interesting number. In mathematics, it has a huge history, and the beauty of -1 in different calculation is sometimes it's really complex, but it gives a very good new tool to calculate lots of complex equation. For example, for differential equation or to work in frequency domain, we have to use the property of -1. So first I come to the point, what is number? Because number is the basis of all scientific calculation, be it mathematics or physics, be it in social science or economics or anywhere. Number is the basic tool to calculate. Initially, number was created. If you see different history in India, ancient India, Mesopotamia, or Greek, initially the number was created for counting purpose. And those numbers we can say are the natural numbers. Usually natural numbers are 1, 2, 3, and you can go for infinity. So we can say that God created the natural numbers, but all the rest of the work using those numbers are by human. So I'm coming, what is real numbers? See in the slide, the smallest set is the natural number. That is 0, 1, 2, 3, and generally it is represented by capital N. After natural numbers, the next one is the integer. Integer you can view it as some reflection of a natural number. Suppose you have 1, so obviously you have -1. Suppose you have some x, some number, obviously you have -x. So after the integer, we go to the rational number. Rational number is some numbers which lies between the integers. Suppose 1 and 2 are two integers, so rational numbers should lie between 1 and 2. And this rational number should be represented by A by B, where the GCD of AB is 1. Suppose take 1 by 2 or 2 by 3. So 1 and GCD of 1 and 2 is 1. Similarly, the GCD of 2 and 3 is 1. So after rational number, it comes to the real algebraic number, which are basically irrational number. So real algebraic number is defined as a number which is the solution of any polynomial equation. Those who don't want to go in the difference between real algebraic number and real number, don't go there, okay? Just consider the real algebraic and real number are something like irrational numbers. So when we are dealing with any computation or calculation in real plane, all the numbers must lie inside this bigger set, that real set. And the property of that number define the number belongs to which set or not. So this real number set can be represented as a real number line. It is very basic concept of the number line. Here 0 is the 0th element, or some books consider 0 is the first element of the real number line. But you have 0, 1, 2, 3. Similarly, as a reflection, around 0, you have -1, -2, -3 also. 0, 1, 2, all are natural numbers. The right-hand side of your graph is the natural numbers. When you will take the full number line, it is integer numbers. Any numbers between 0, 1, 1, 2, 2, 3, it is the rational or irrational number. So when we get some simple mathematical properties like addition, subtraction, what we will do? We go along the number line. Suppose we want to add 1 and 2. We will go to 1, then we will go 2 times 1 and again 1. So it becomes 3. Similarly, if we subtract 4 minus 2, I have one number 4 going from 0, 1, 2, 3, 4, and I have to subtract 2. So I am coming back side 2 times, so I am getting 2. The subtraction and addition is very simple in number line, but the problem comes when it is the question of multiplication. The problem of multiplication says that it is the lot of number times of addition. So if we add 2 into -3, so I have to go 3 times with unit distance 2. Similarly, if we have to create 2 into 3, we have to go positive side into 2 into 3. Here, there is no problem because you get one positive integer and one negative integer. So, our multiplying integer rule says that when we are multiplying to plus, we get plus. If we are multiplying plus on minus, we get minus. But the biggest problem, when we get multiplying to negative term, how should we get +1? Because in number line, you cannot say that you have to go -1 times. So the multiplication rule in number line does not hold. So the simple question comes, why -1 and -1 brings +1? You cannot prove this statement using simple addition rule on number line. So we are going one step further. To prove this statement, we need a real number set, that is R, which are already shown here, and we need 3 types of operation. One is plus, one is minus, and one is cross or the multiplication operation. And this type of operation have different type of rule that is available anywhere, the distributive rule, all these things. So to prove that why -1 and -1, let's say there exists a number y, which is represented by a cross b plus minus a cross b plus minus a cross b. Since a and b are in the same set, so any type of operation between a and b will produce a number which should belong to the same set, and that number should be unique. So we can represent it y as a taking b as a using the distributive law. We're taking a plus minus of a cross b plus minus a cross minus b. It gives you 0 into b plus minus a cross minus b. So it becomes minus a cross minus b. Similarly, if we take the distributive law in the last 2 part of that y, that is b plus minus b, and minus a becomes common, so we will get a cross b plus minus a cross 0. So it becomes a cross b, hence we can say A cross B is actually minus A cross minus B. But you cannot prove in number line, that is, it is a minus 1 or minus A time of addition. And that is the beauty of minus 1. You cannot prove directly without help of set theory or group theory that y minus 1 into minus 1 is plus 1. So when you know the minus 1 into minus 1, you can play with their power term. Obviously, minus 1 square becomes plus 1. If we take another minus 1, it becomes minus 1. Hence, you can generalize for any integer n, minus 1 whole to the power 2n is plus 1, where 2n is the integer and 2n plus 1 is minus 1. But the problem comes when n is not an integer but a fraction. And that is the another beauty of minus 1. Root over minus 1, it is one of the most confusing representation of mathematics. Really what it means, nobody knows, but it exists. And it is one of the biggest tools to calculate complex problems. Generally, mathematicians define root over minus 1 as a I. You cannot count I. It is not a natural number. It is not an integer, obviously. It is not any rational or don't have any rational or irrational behavior. But it exists and you can play with I. At this moment, we say I exists, but what is I? We don't know. Generally, any axis which is perpendicular to the real line axis is the imaginary axis. And this plane is known so-called Argand plane or Argand, and this diagram is known as the Argand diagram. So any number, any complex number can be represented with real number and some real number which has some operator I on it. So now my full number set is changed. Initially I have a big real number set. Now we will say real number is a subset of complex number. We have some I, this set, we have some real number set, and put together we will make a complex number. It is very well known, and in this presentation I am dealing with only complex number. Those who want to go beyond, there is we call hyper complex number, and which is very much useful in computer graphics. Those who are interested, they can go the hyper complex number, and there is a different type of algebra we use, that is Clifford algebra. I am not going to that Clifford algebra and hyper complex plane. We are now on complex number. But complex number, this real and imaginary axis, it gives a new definition of number. One part of is known, which is countable, and another part is unknown. So Leonhard Euler gave a very beautiful representation to relate the geometric nature of the complex number. If there exists a number here which is making an angle phi with the real axis, then real axis, this part is cos phi and this part is sin phi. And he gave a very beautiful representation, that is e to the power I phi is cos phi plus I sin phi, where e is Napier logarithm basis. It is very useful formula, and lots of times we use in different domain, in computation or complex number, anything. The first thing comes in the mind, why e to the power I phi equals to cos phi plus I sin phi? Is there any proof? There is a lots of complex proof representing the series representation of cos phi and I sin phi. I am not going in detail in it, but in this presentation I am showing a most simple proof of Euler equation. Just consider there exists some function which is represented by e to the power minus I phi into cos phi plus I sin phi. Now just differentiate the function with respect to phi, you will get 0. So any change of function of phi with respect to phi is 0 means the function of phi is constant. Since f0 is 1, you see that since f0 is 1, you just put the value 1 there, you will get 1, cos phi is 1, I sin phi is 0, so I cancel out. So f phi is 1 for all values of phi. Hence, ei phi is cos phi plus I sin phi. It is one of the simplest proof of the Euler equation, and it gives a really good relation between three beautiful constants of mathematics. That is E, that is Neperian logarithm base, I, which is imaginary number, nobody knows what it is, but we use it, and pi. It is simply the ratio of the circumference and the radius of a circle. In the previous equation, if we, in the place of phi, if we put the value pi, you will get e to the power I pi is equals to minus 1. This equation, it is the one of the beauty of mathematics which relate three important constant of mathematics, E, I and pi, and their combination gives the value minus 1, which is real. So similarly, if we take the over root in both sides of e to the power I pi, we get e to the power I pi by 2 is basically root over minus 1 equals to I. So in any type of calculation, we should not use root over minus 1 because we can just represent it as I, and we can take I square equals to minus 1 and we can do the calculation. One of the good application is that lots of people say there exists no logarithm of negative number, but logarithm of negative number exists in complex plane, not in real number plane. Since in Euler equation you can put 2n pi and get minus 1, so logarithm of any negative number can be represented as log of x, that is its principal value or the real value of this term, plus I 2n pi. The most interesting fact is that since n is integer and can take any values, the negative logarithm is not one-to-one value. That it can give, log of any number can give infinite values. And it is the end of my presentation.